Okay, it's lecture 16 of our computational microelectronics 2024. So let's get started. So up to now, we have discussed about the process simulation related with the diffusion simulation. At the end of our previous lecture, we have just introduced certain things like consideration of electric field effect. So in order to introduce this electric field effect, actually we had to introduce another term called as drift, and that was related with certain things like gradient of electrostatic potential. This is related with the electric field. So that was done in our previous process simulation, diffusion simulation. But today we will talk about the other one in the computational microelectronics, device simulation. So in this case, instead of considering the diffusion of a dopant or change of shape, we assume that device, the structure under simulation is given. So this is just given from device simulation or other means, so it is fixed. And when we perform the device simulation, our goal is to characterize the electrical performance of this device. Simply speaking, we wanted to calculate this IV characteristics of a certain device structure. Even in this case, we found that actually the simulation principle is more or less similar to that of our previous process simulation. But at that time, the species of our interest was was dopant density. But now instead of that, we wanted to know something like electron density or hole density. These two quantities are of our interest in the device simulation. And please note that dopant is the atomic core, so it is more than 10,000 or 1,000 or 10,000 times heavier than electrons and holes, so their movement are quite slow and can be observed only at elevated temperatures. However, in the case of our electrons and holes, they are quite light in terms of mass, and even at room temperature they can move quite fast. So that's the reason why our simulation or the time scale considered in these two calculation or simulation are completely different. So simply speaking, in this dopant diffusion simulation, we had to quite high elevated temperature, and we need long time. And in terms of device simulation, this can be obtained even at 300 kV or even below, and short time scale is required to get an equilibrium condition. Okay, anyway, it is certain that both cases we have to solve continuity equation. So now let's go to this lecture material. Electrons and holes, they are our quantities of interest. So how can we calculate those quantities? When we consider nonlinear Poisson equation, so I think that already you have done it for your calculation for electric field in the diffusion simulation. But anyway, in the nonlinear Poisson equation, we assume that electron and hole their densities can be expressed as in terms of electrostatic potential. Please note that these expressions are valid only at equilibrium. So if we go a little bit further, then if we wanted to generalize it to more general cases, then we have to introduce some quantities like this or some quantities like this. So these quantities here written with phi but with underscores, so they are called as quasi-Fermi potential. Of course, depending on their subscript, one is electron quasi-Fermi potential and the other one is a whole quasi-Fermi potential. In the case of equilibrium case, the case we have considered in previous lecture, in this case we were allowed to set these two values as just 0 volt. So that's the reason why, although in general electron density can be written as in terms of phi minus phi n or phi minus phi p, so although these quantities are important, but with this special consideration at equilibrium, then we can safely neglect these two terms, and electrons and holes are just expressed in terms of electrostatic potential only. So that was the situation, and I hope that all of you guys in this classroom already solved this nonlinear Poisson equation, and you can now calculate the equilibrium electron density. But point is, that was only done at equilibrium condition. However, in the case of our device simulation, so main goal is calculation of IV. So this non-zero, non-vanishing electron current or electric current means that this is just a non-equilibrium case. Of course, if our system is at equilibrium, then current would be just 0 without any ambiguity. So that is given, but now we have to introduce certain electric current by applying certain voltage difference at terminals. Okay, so therefore, simply speaking, at non-equilibrium cases, we need a general method to calculate electron density and hole density. This is no longer valid at non-equilibrium case, so we must solve additional equations for electrons and holes, and the answer is yes, we must solve a continuity equation. Then maybe you can ask me this question: even when we consider process simulation, diffusion simulation, we considered this continuity equation. So do you remember, for diffusion simulation we had to solve continuity equation for dopant density C, and now we must solve continuity equation for electrons and continuity equation for holes, so they share the same form. It is because nothing but this continuity equation is quite general. So continuity equation simply means that if your particle of interest does not create it or does not annihilate it, then this will be the case of our equation. Simply speaking, continuity equation means that if we have a certain area, and there can be many different ways to change the number of particles inside this box. But one possible way is just to add more particles through 6 surfaces or 6 faces of this small box. That is one way to increase or decrease the number of particles. And another way is just to create it. So previously there was nothing but just to create one particle or annihilate it. So this pre-existing particle is just gone. So in that case we can change the number of particles inside the box. Continuity equation here in this form, so sorry, it stopped. Okay, so continuity equation in this form simply means that if we don't have this generation or recombination of particles inside our system, then the only remaining physical mechanism to change the number of particles is just a physical movement in the real space. So now think about, or I always think about this one. Here we have a certain country, yes, then please try to trace the change of population. So how can we have, for example, let's say that there are 50 million persons in a certain country, then how can we increase the number of persons? So one way is to make births with newborn babies, then we can increase it. And if some guys died, then there will be the decrease of density or number of total population. That is quite easy to understand, but another way to increase the total population is to allow immigration from other countries. Then we can increase the number of population. Quite similarly, it's just like this example. Here we have a small box, and in order to increase the number of particles, there are two different ways, just to creation or annihilation. That is one thing. Another one is physical movement of particles from the neighboring boxes. So we are now talking about this one. In this form, the right hand side, the divergence of particle flux, particle C type, is given as just a physical movement of particles, and actually, so this term itself, divergence of flux, is physically defined to set net decrease of our particles inside the box. Actually, net decrease, why we have a net decrease? Because this one flux is defined by performing this action. Actually, we can count the number of particles escaping from these boxes. So here we have a minus sign in order to make a net increase. And simply speaking, if we read this equation, and so simply let me just write down temporal, time dependent increase of C density. This is the left hand side term of our equation. Time dependent increase of our particle density is determined by net incoming flux of C particle. Okay, so in my sentence, temporal increase of C density, this is corresponding to the left hand side of our continuity equation, and the net incoming flux means the right hand side of our continuity equation. So when I say C density, then I have not made any assumptions about the particular properties of our C particle. What should be the C particle? Is there any restriction for this C particle? For example, only electrons can be considered, or only holes can considered, or only, for example, atoms, phosphorus atoms can be considered. Actually, you really understand when I say this argument, I'm just saying that just a movement of something. So this C, what can be C, is completely arbitrary. So if it does not created, it is not created, or it is not annihilated, then we can take any value or any particle as the C particle. So simply speaking, that's the reason why continuity equation can be applied to the atomic diffusion and also motion of electrons and holes. Even, for example, I have shown you this problem. So at the time, the particle of human was treated as a particle. It is possible because, in this case, this description is completely arbitrary. And even, for example, let's think about this one. This is our road, and if we have cars on the road, and if our road system is quite a complicated shape, and there is a certain wasteland, and let's say that this is the road shape. Even in this case, we can apply continuity equation. We neglect the events like suddenly a car pops up from the ground, or car disappears from certain point from the road. If we do not consider such kind of unusual events, then even for cars on the road, we can apply continuity equation. You understand? As much as we can identify certain type of particles or certain quantities, and if the dominant mechanism for changing their number is given from net movement or transport, then we can apply this continuity equation. So following this argument, now we wanted to apply electron and hole as the C density. We wanted to take into account the motion of electrons and holes. Then, although it is quite general, all of details are just hidden here. So flux, what is the appropriate form of flux for C density? That is the key point. Since this continuity equation is so general, so basically this is regarded as just a given one. But point is, depending on your model, actually you can find many different forms for this particle flux C. If you have quite complicated model, then you will have quite complicated form of F sub C. And if you have a simple model, then you will have quite a simple expression. For example, one simple form you have already seen was this one. Do you remember? In this case, that was the dopant density, and this was the diffusivity of your dopant. And this one just contains only diffusion simulation or diffusion component. So you think that, okay, in this movement of our dopants, they are just primarily determined by diffusion mechanism. So that was our assumption. Of course, when you solve your system with this flux, it means that you have completely neglected the electric field effect. In order to consider this electric field effect, then you must add more terms to your flux term. So that was the situation we have to consider. And before introducing the form of our flux for electrons and holes, so we, simply speaking, we have to consider electron flux and hole flux, but sometimes we wanted to use a little bit different related terms. Instead of electron flux and hole flux, sometimes we wanted to talk about electron current density and hole current density. This is because eventually what we wanted to do is to calculate electric current out of this simulation. So that's the reason why from this flux, this is flux and its unit is, so number of particles crossing a unit area at unit time period, okay, per second, per square centimeter, how many particles are crossing. This is the flux, the unit of flux. Instead of that, so current density here have the unit of ampere per square centimeter. Okay, it means that per unit area, what is the density of current? So you can easily understand, if we make certain area integration of this current density vector, then we will have, this is ampere per square centimeter, and this aerial integration gives us another area scale, so we will have just ampere scale quantity out of this integration. So it is an easy way to calculate the current out of current density. So simply speaking, our goal is sometimes to calculate drain current or source current, gate current, blah blah blah. All kinds of these terminal currents are of our interest. So in order to calculate this one, we ask ourselves this question. Okay, if we wanted to calculate the drain current, then we must integrate the current density over drain contact. If we wanted to calculate the source current, then we must integrate the current density over source contact. So we need these current density vectors. So then how can we calculate this current density? Okay, current density is closely related to the electron flux and hole flux. Their relation is simply given as this form, linearly proportional. So Jn, electron current density, and hole current density is simply given as minus Q, because here minus Q represent the charge carried by an electron. Quite similarly, if we consider JP and FP, in this case, a hole carries just a positive Q when it moves, so we must have positive Q. So although we have different charges, so but they carry absolute amount of positive Q, and depending on their polarity we have a minus sign or positive sign. So anyway, if we wanted to calculate the drain current, let me repeat once again. If we wanted to calculate drain current, then we must know the current density over the drain contact. However, selectively finding out the current density only at the drain contact is not possible. So we must find out the current density all over our entire simulation domain. Then how can we solve, or how can we calculate this current density vectors all over our entire simulation domain? Simply speaking, since J and JP are related with fluxes, so by solving this continuity equation, then as a result of this solution procedure, we can calculate electron flux all over our simulation domain and hole flux all over our simulation domain. Once we get these numbers, okay, these vectors, then we can recover Jn and Jp, and by integrating this Jn and Jp over our integrated terminal or interested terminal, then we can eventually calculate the terminal current of our interest. Drain current, source current, gate current can be calculated. Okay, do you have any question? So why we have to have all kinds of these calculation? The reason why we have to do it is just explained. So in order to calculate the drain current, simply speaking, drain current itself is just a scalar quantity with ampere scale. It's like just 1 microamp or 1 nanoamp. So this is just a simple scalar quantity. However, in order to get this scalar quantity, then we must calculate the current density vector all over our simulation domain. So this is quite much computationally heavy. So let me just draw once again. Let's say this is our device. This simulation domain, the entire simulation is just written as omega, and let's say here we have source contact, and here we have drain contact, and of course we have other contacts there. And what we wanted to do is just to calculate, yes, this drain current, and drain current is just heading in this way. Okay, what we wanted to do is just to integrate current density vector only over this short range covered by the drain contact. So if we can selectively calculate this current density vector on the drain contact, that will be perfect. If we have any certain way to selectively calculate these quantities only. However, unfortunately, if you wanted to know the current density at this point, this is closely related with the current density at this point and this point and this point. So the entire system is just connected through this continuity equation. So we cannot just divide the system and solve only drain related part and source related part. It's not possible. So that's the reason why we must consider the entire system and solve the continuity equation. So I hope that it can be helpful to understand the motivation of this quite complicated solution procedure. Okay. So then in the device simulation, of course, there can be many different forms of current density. So there have been many different forms, but let me just show you the simplest one and the standard one. This one is called as drift diffusion. So when you have a look at this form, these two forms for electron current density and hole current density, you can identify two different terms. One term is related with gradient of your particle density. This is called as diffusion term, and you can identify also another term related with gradient of phi. You know that minus times gradient of phi, that is just given as electric field under the electrostatic assumption or approximation. So now you can understand the first term in the right hand side is corresponding to the electric field. So this is called as drift term. So that's the reason why this form is called as drift diffusion. So now the entire model is called as the drift diffusion model. So although we are saying that drift diffusion model, there can be many different models, other model, so several of them. But interestingly enough, all of them share the same equation. This equation, continuity equation, is solved all of these variants. However, why this entire system is called as a drift diffusion? Because since solving the continuity equation is shared and it does not give us any distinction between different models. One model solves only drift diffusion. One model additionally consider another physical mechanism, another one. So depending on these details, they are classified or named as different models. Okay, so when we come back to our standard drift diffusion model, so now it contains two terms, but it doesn't have any terms related with gradient of temperature. So it means that now you have here hot region and relatively cold region, and if you have this kind of a temperature gradient, actually you can find also net flux of your current. However, in this case, you don't consider this temperature gradient. It means that actually your equation cannot be applied when the temperature profile varies across our simulation domain. So it means that, for example, let's just come back to our conventional MOSFET. So now here we have source and drain, and let's assume that we have applied a certain voltage called as a VDD to our drain contact. So then what will happen? In this case, there will be net movement of electrons from source toward drain contact, and this is corresponding to J sub n. Also, what is the difference of the potential between these 2 points? You can easily understand potential difference is given as a VDD. So think about this one. You have current, and between these 2 points you have voltage difference. So simply speaking, it's like this. Here you have 2 points, one and another point, and here you have current I and voltage difference V. Then what will happen? If you have current and voltage difference, it means that you will have power dissipation given as voltage difference times current. So that will be power dissipation. So here power dissipation means that conversion from the form of electric energy to the other energy form, like heat energy or other types of energy. So simply speaking, since we have voltage difference and current conduction, so there will be certain power dissipation. The power dissipation means that now electron lose its energy and it is transferred to the lattice system. Here we have a silicon lattice, and now this silicon lattice takes a certain energy from the electric system. So what will happen? In this case, a part of a certain point inside this device will have excessive energy than the ambient temperature. For example, let's say that we are working at 300 Kelvin, and now we have quite a good metal plate here. So since this is really good metal, so for example, this plate is regarded as just 300 Kelvin. So what we can expect is every point in this system actually have the temperature of 300 Kelvin. However, by just operating this device, a certain part of this device is locally heated. Means that because the source of this heating is just power dissipation of our electron system. So simply speaking, if we consider our system, yes, this part is locally hot and other part is locally cold. So what will happen? There will be also change of electron transport according to this local temperature variation. So when I say temperature here, what is the temperature? This is the temperature of our lattice. Our lattice means that silicon lattice system. So simply speaking, when you come back to our equation, we don't have any terms like gradient of temperature. It means that that effect is not included in our drift diffusion model. So it is not included. So this temperature gradient is particularly important nowadays. So you know that in reality, in industry, we are now talking about HBM, high bandwidth memory, and when you have a look at that device, actually there is the stacking of different memory dies, and they are just concentrated with really compact form. However, we allow or we make quite frequent frequent information transfer from HBM to GPU. In this case, we have to send the data through this stacked die system. Here we have multiple dies, and certain information from here should be transferred. And although we say that information is transferred, it means that actually electrons should move. In this case, there will be quite a high electron density, current density, and locally there can be heating up. So even in this case, inside our chip, there can be significant, that's really significant difference of temperature. For example, if we go to the packaging, and this is just corresponding to the ambient temperature. However, inside it, it can reach, for example, almost 100 degrees Celsius, or even higher. In that case, actually the properties of materials or electrons inside it at 300 Kelvin and or at more elevated temperature are completely different. So nowadays, consideration of temperature gradient is quite important. However, please note that this is just the beginning of our device simulation. So in this case, we think that current density J is not that high. So that's the reason why the generated power or power dissipation by this J is also not that high. So temperature is just quite close to this ambient temperature. So we don't have to consider temperature gradient. That is the basic assumption we have used in this distributed diffusion model. Please note that we are now following the historical development of our models. When they first makes this kind of simulation techniques, the device was quite large and current density was not that high. So also we have quite much spaces, so they are just loosely placed. So at the time they saw that it is quite tightly placed, but compared with today's device, that was quite loosely packed. So we were able to neglect all kinds of these effects. However, situation has changed quite a lot for during several decades, and nowadays you are now living in the era of many different physical considerations. Physical effects should be included in your device simulation. That is the world you are currently living in. Okay, so anyway, let's go to this one. So you may find that this is quite similar with our previous dopant diffusion simulation. So at the time we have considered the electric field effect, and actually yes, it is identical with that form. Nothing. We have seen similar expressions before. Yes, it is because yes that they share the same thing. There are particles, and these particles are moving. Since they are charged particles, they are pushed or attracted by the electric field, and when they have temperature or density gradient, then they diffuse. All over our dopants and electrons and holes share the same physical mechanism. That's the reason why we must solve the same problem. However, the techniques are a little bit different because the scale is different. Okay. Then this slide, so page number 6, just to discuss about derivation. How can we justify the use of continuity? So although I say that just to I have shown you the certain analogy to the population system or road system or something like that, all kinds of my arguments to use continuity equation was just a certain not rigorous argument. So I'm just showing that okay, let's make an analogy to this another physical system, and that can be just expressed the same form. However, please note that all of these continuity equations can be rigorously derived from more rigorous equations. So this is Boltzmann transport equation BTE, and this is the governing equation of semi-classical transport, and continuity equation can be systematically derived from this more fundamental equation. So we are not introducing the continuity equation without any ground. So there, although we do not consider the derivation procedure detail, but we can do it. So if you are interested, please refer our previous lectures, or previous means that so lectures 1 year ago, 2 years ago, something like that. Also, you have references. Okay, so now, so without explaining the details, so we just understand or accept the validity of a continuity equation, and we wanted to solve it. So let's just dive into the solution procedure. So here we have an important difference between our device simulation and other previous dopant diffusion simulation. In many cases in the device simulation, first we consider steady state. Steady state means that simply all kinds of these time dependent quantities go to 0. Yes, so if we consider the dopant diffusion simulation, if we allow the infinite time for our simulation, then actually the uniform dopant density will be the steady state solution. If we wait for a while, long time, then eventually, since the driving force of our dopant diffusion is density gradient, the change or spatial difference of density, so that will be gone, so we will have a uniform distribution. However, in the case of our dopant diffusion simulation, we do not wait such a long time because we wanted to make some non-uniformity of dopant profile intentionally. But think about this electron system. This electron system is so quick, so within nanosecond or picosecond, this system always find out its steady state behavior. For example, previously you applied just 0 volt to your transistor. Well, that was a certain system. Suddenly you increased the voltage up to 0.7 volt. So it introduced a huge difference in its boundary condition. So what will happen? It means that the device will take some time to reach at a new steady state solution. But please note that in our modern device, it is just the orders of a nanosecond or picosecond to arrive this new steady state. So it is really difficult for you to see the transient effect for modern scaled device. So it is a really good approximation that the device is always at the steady state. Then, if you really wanted to see this transient effect, you must see a little bit different cases. For example, if your oscilloscope is really fast, so if you can just measure the time variant of your electronic system within picosecond scale, then maybe you can see the changeover. However, this is really difficult to find out because this is in the measurement of such kind of behavior is really difficult. Another way to clearly see the transient effect is if we have a certain slow system inside our transistor, then we can see the slow change of our transistor behavior. One good example of this kind of a slow procedure is your memory device. Let's just think about NAND. In this NAND device, actually in order to change the threshold voltage of your NAND device, actually you must apply several millisecond pulses into your cell. Then why it is so slow compared with the nanosecond or picosecond? Because this is the response time of our electronic system inside silicon material. They are really quick. However, NAND, in this case, the time scale is not determined by the motion of electrons inside the polysilicon channel, but it is determined by from polysilicon channel into nitride region. Here we have silicon nitride region, and this amount of electron injected into this silicon nitride region determines the threshold voltage of our NAND cell. So it is this current density is so low, so small, so it takes quite a long time to have meaningful difference of our physical quantity or electrical quantity. So please understand what is the proper description about our system. It really depends on the system of your interest. If your system is so quick, then maybe steady state approximation is always a good choice. However, if your system has quite a slow variation inside it, then actually you will see the change, and that's the reason why you must trace the time variance. Now let's come back to our dopant diffusion. Is it fast system or slow system? From our discussion, you understand dopants react quite slowly from our point of view, so that's the reason why we must trace their temporal variation step by step. But in this case, electron system can be regarded as quite quick, so our first interest laid on the steady state one. In this case, actually we had to solve, although we had to solve this continuity equation, but under the steady state approximation, this left hand side term can be safely set to be 0. So we will have just vanishing divergence of our flux. Also, please note that since we have this kind of relation, so they can be also written as this form, plus minus Q over JC that is the form of our continuity equation with current density. I think that is more prepared way you see in the literature instead of flux. In our many references, the continuity equation is written with current density. So sometimes it has a negative sign and positive sign. For example, let me just explicitly write down here. So if we consider electron continuity equation, then in this case negative sign is involved, so we will have 1 over q of divergence of Jn. That will be the form of our electron continuity equation. On the other hand, if we consider whole continuity equation, so you will have this form, minus sign here. Okay, so here, that is the one you have to keep in mind. So complicated polarity difference comes between electron expression and hole expression, and sometimes students are confused with whether I should add a minus sign here or there. So please don't be try not to be confused. And here we have this form. Yes, this is the continuity equation. The time derivative of electron density is given by 1 over q times divergence of Jn. And under the steady state approximation, it just vanishes. And 1D case, we can simply write it down in this way. Okay, so this is not that difficult, and its discretization is just following the typical way. Here I wanted to say quite an important point. Okay, so in 1D we can write down in this form. It contains both of first derivative of electron density and first derivative of electrostatic potential. Well, so in next page 8, I just introduce some way to discretize it. Simply here we have dn over dx. That is just approximated as delta x n minus n. Also here we have d phi over dx. This is discretized with phi minus phi. So are you with me? So since we have first derivative, each of them is treated as usual. Then point is, now here we have n. Then what is n? This is electron density, but think about this one. Here we have a segment. This is x sub I, and this is x sub here we have x I plus 1 and right now we are calculating this first derivative at the midpoint between them. Okay, in this case we calculate dn over dx and d phi over dx. Good. Then what is it? This is nothing related with the first derivative, but just n itself is required. Then which n should be used? For example, you can try n at x sub I, or you can try n at x I plus 1, or you can also try the half of them, the average between these two numbers, xi and xi plus 1. In this presentation material, I just urge you to use average of them. That sounds really reasonable, because the evaluation point is just midpoint. So if we have any coefficient, then that coefficient should be calculated at that point. But you will later find that this is a really important step. Okay, but anyway, here we have used just average electron density between 2 points. So after that, every calculation can be done quite straightforwardly, so I will just skip all of these one. Okay. The reason why I'm skipping is you are already done several experiences on similar problems in the diffusion simulation. So for example, even when we consider this system, we can consider electron continuity and hole continuity separately. Okay, here we have electron continuity and hole continuity. Previously, you have considered something like this. You have considered arsenic continuity, also boron continuity. Quite similarly, you can consider electron continuity and hole continuity inside a large system containing both of electron density and hole density as a solution. Also, you can integrate you will also include the Poisson equation in your system too, so you can generate a grand system. So let's say that if you have capital N points, then the number of unknown variables inside your new system is no longer n, but number of unknown variables will be just 3 times n. Why do we have 3? 1 n for phi, 1 n for electron density, and another n for p density. So you can generate a large system and apply the same method to your problem. So I just let you solve equilibrium case first. So please consider a p-n junction. So this p-n junction has the symmetric doping density 10 to the 17 per cubic centimeter. Both of donors and acceptors have the density of 10 to the 17 per cubic centimeter. And the metallurgical junction is placed at 200 nanometer in this position and set 400 nanometer as the entire simulation domain. So of course, if you wanted to have a bigger one, so instead of 400, I wanted to have 1 micrometer, yeah, that doesn't matter. But please do not reduce it further. If you reduce, for example, in order to save the simulation time, I just wanted to introduce 200 nanometer. Then that will destroy your answer. For example, then you will have this profile, and at this point, the system is no longer corresponding to its neutral rhythm. So please do not reduce. So for this system, so now you have what I will show you what you have to do. For this system, this p-n junction, first solve the nonlinear Poisson equation. I hope that already all of you have done it for different situation. So I think that you can also solve the nonlinear Poisson equation. So now you have correct solutions: electrostatic potential and electron density and hole density. After that, just to try to solve the drift diffusion model. What is drift diffusion model? This is nothing but the collection of your Poisson equation and electron continuity and hole continuity. One thing you have to understand is, when we say drift diffusion model, it contains Poisson equation, and this Poisson equation is slightly different from the Poisson equation, the form of non-linear Poisson equation. So in this case, when we say the non-linear Poisson equation, we express our electron density and hole density in terms of electrostatic potential. But in the case of drift diffusion model, please don't do that. Your Poisson equation must have electron density and hole density in it, instead of expressing your electron density and hole density with these electrostatic potentials. And using this electron density and hole density, please make the system. Since the solution of your nonlinear Poisson equation is also a solution of your drift diffusion model, so you will have the immediate solution. Why we do that? Because we are just preparing ourselves to expand it to non-linear non-equilibrium cases. Okay, let me quickly cover the remaining one today. So now I think that by performing this exercise, now you can solve the equilibrium solution. However, equilibrium solution can be obtained just by solving nonlinear Poisson equation. Actually, we don't have to solve the full drift diffusion model for equilibrium case. But point is, now equilibrium or non-equilibrium case can be solved by the drift diffusion model. So please also solve the drift diffusion model at non-zero bias condition. So you can just do it. In this case, only difference is the anode contact voltage is now changed. Previously, its applied voltage was just 0, but now you can increase this anode voltage. So, for example, by applying your Newton iteration, you can get the solution, and the answer will just look like this. So here in this case, if here voltage means that your anode voltage. If your anode voltage is positively applied, then you will have exponential growth of your anode current. And if you go to the negative one, like anode voltage is negative value, then sorry about that, this is just a forward one. And if you go to the negative one, then you will have almost nothing. This is 10 to the minus 16, and you can see that here this is just orders of one milliamp per micrometer square. So there is a huge difference in the current conduction. Depending on the polarity or sign of your applied voltage, your system shows quite much different behavior. Okay, So let me just announce the homework number 16. Homework number 16 is particularly important. So previously, homework number 15 was the end of our dopant diffusion simulation. And now homework number 16 is related with the starting point of your device simulation. So please calculate IV characteristics of a PN junction. So simply speaking, please try to reproduce the graphs shown in page 17 and 18. So in this case, of course, you need the mobility values, and for electron, please use this relatively high value, and holes, please use a relatively low value. So now you can solve this system. Details of implementation already summarized in this lecture material. So for example, if you wanted to know the correct form of a Jacobian matrix, then please have a look at, for example, the Jacobian matrix, or yes, you can find this one. This is corresponding, for example, this is only for J sub n. However, you can also find similar expressions for J sub p, and please try to implement it. I'm afraid that actually when you make mistakes in your implementation, you will see the convergence problem. Okay, so that is quite a typical case students can have. So if you have a convergence problem, then please try to fix the problem. So since this problem is a proven problem, solved by so many different guys already, so if there is something wrong, so maybe that is your mistakes, not the deficiency of that problem. So there can be so many different cases, but what I want, my general advice on solving this problem is quite simple. Sometimes you have a convergence problem, then don't panic. First of all, please identify the root cause of your convergence problem. Root cause means that when you have the Newton-Raphson method, always you construct Jacobian matrix and residue vector, and by solving that system you get the update. And in many cases, the update is so simple. Once you have a solution, just to make the subtraction between your original solution and update. So this is not the case you make mistakes. Frequent mistakes can be made when you generate Jacobian matrix or when you make the residue. And please note that the Jacobian matrix and residue vector should be consistent. If they are not consistent, then there will be certain convergence problem. So please note that first of all, when you have some convergence problem, then first of all you have to see what is the position of the error occurs, and if each of them, Jacobian looks perfect and residual looks perfect, then please check the consistency between them. Are they consistent? Also, since J and JP have slightly different sign convention, so please not to make the wrong sign in your Jacobian matrix. Only one single sign mistakes can introduce severe degradation in your convergence behavior. So it's a little bit tricky, so please try to do that. Since this problem is so important. Please do your best to solve this problem. Once you can solve this homework number 16, then I hope that homework number 17 will be much more easier. Is homework number 17 will be devoted to the use of well-known Shapeta Gumne scheme. So this is actually the most important part of our entire semester, homework number 17. But if you can perform this homework number 16 without problem, then that can be a really good stepping stone to achieve the successful homework number 17. I hope. Okay, so thank you for your